So the y's component, due to unbalanced this tension, can be written as t d square y dx square dx, okay, is positive y direction, and plus we have fxt dx, considering that fxt is the force per unit length acting on the string, okay? And that has to be equal to rho L dx d square y dt square. Therefore, what I got is d square y dx square plus fxt divided by t is equal to rho L divided by t d square y dt square, and that is the inhomogeneous governing equation for a string, right? You can do it when you have a time. Of course, I would not ask you to derive this during the midterm examination, but the only reason why I'm doing is to show how this minus comes. Rearranging this equation, and I have a minus c square, because the c square is t over rho L, right? And I'm moving this one over here, and then I have minus 1 over t fxt, right? Okay, same things would happen for one dimensional acoustic wave. That's why I have a minus. But if you are very uncomfortable with this, then forget it. Then the force you are considering over in this term, when you do not have a minus, means that the force acting negative axis. It just only, you have to be concerned very much on the sign only, right? But if you use minus over here, this force is force acting on positive x direction. Okay, if you look at another text, you might have some other scale factor over here. Okay, you can see some scale factor over here, like the scale factor over here. If you drive a similar way, then you will see some scale factor over here too. But I mean, that scale factor doesn't really matter, because if we consider that as a part of our excitation term. Okay, so this is quite general. This is a quite general acoustic wave equation. So I will make some box over here. Now, our job is solve this equation, right? To find out pxt. That is our job. Of course, what you can do is using Green's function or eigenfunction approach, right? So again, I emphasize again, our job is solve this inhomogeneous partial differential equation, either using Green's function or eigenfunction. Of course, we have boundary condition over here. Find out the solution that satisfies the boundary condition. That is our job. Okay. However, what I can do, instead of using Green's function approach or eigenfunctions approach, I can think that, hey, the equation, this equation, governs the interior of the one-dimensional duct. Case one, right? You had a hard time last night? Okay. Assume that I want to find the solution between x equals 0 and x equals L. Okay. For infinity case, as we saw in before, the solution can be either plane wave or superposition of many monopoles and so on. That is the special solution, and we studied that already, right? But what if there is some excitation and I want to find the solution between x equals 0 and x equals z? For example, that one has impedance at x equals 0, z0, and x equals L, zl. Right? Maybe I will extend this concept. I want to find out the solution that satisfies the boundary condition over here, that is GS. So boundary condition is different along this surface. And I want to find out the solution inside of this enclosed volume. Eventually I want to extend this concept to here. And this will be done very extensively when we study chapter 4. So what I'm teaching today is sort of introductory. I'm trying to introduce the basic concept, and I want you to grasp the basic concept. Okay, what I can do is say, let this is equation 1. Okay. And then what I can think is that the solution of this would be the solution, superposed solution. For example, if I have this kind of excitation at x equals 0, in other words, if I have Dirac delta function at x equals 0, and obviously the dimension of this and this, or this has to be p. That is more sensible. And I will denote this is G. G is solution, in other words, the pressure that is induced at x due to the impulse at x equals x0. Okay. Okay. And because this force can be expressed by integration fx0 t delta x minus x0 d x0, right? Using delta function, right? So what I'm saying, what I'm trying to do is, if I know the solution due to this excitation, then because this is just the superimposition of the response due to delta function, then I might be able to get the solution due to general fxt.